So let's talk in some detail about Newton's force of gravity. And before we really kind of delve into this, I'm going to write out the equation. So again, Fg is equal to G, which is the gravitational constant, the mass of one of the objects, the mass of the other object over the radial distance between them squared. Again, from the previous video, we talked about this is an inverse square law relationship. And I am going to explain how this gravitational force for all the equations we're going to be particularly looking at when we write Fg, for example, of a force falling on Earth's surface, it's going to equal the mass of that object times g, Earth's the acceleration due to Earth's gravity, which g is equal to 9.81 meters per second squared. Okay, so we're going to kind of get how does this get this essentially. To explain that, first we got to understand what g is. G is the gravitational constant of our universe. So to really better explain that, I would say it's the intrinsic gravitational strength that has to do with our universe. So, and we've been able to calculate this from measurements and experiments. Our current best estimate of it is 6.67. There are a few more decimals if we want to be really, really accurate. For this course, these first few decimals are going to be sufficient. The units, though, are going to be important. We're going to take a look here at the units. The units of which are meters cubed per kilogram meters, not meters, sorry, seconds squared. Seconds squared, okay? This is important because if we haven't really explicitly talked about it, but a Newton, 1 Newton is equal to, if I think of Newton's second law, F equals ma, it's equal to a kilogram. A is acceleration in meters per second squared. Meters per second squared. That is what a Newton is defined as, okay? You can think it, again, it's the mass times acceleration of an object in terms of its units. And the great thing about physics I love is that the units will always cancel out if you set an equation up properly. The units cancel out with what we need them to be. In order to understand Earth's gravitational acceleration being 9.81, we're going to expound this equation. So gravitational equation between a mass and Earth is going to equal gravitational constant. The mass of Earth we'll call m1, so I'll maybe call me as the mass of Earth, and then we'll do a little m for the mass of an object falling towards Earth, right? That's going to be accelerated down towards Earth, divided by the radial distance squared. Well, if the object is on Earth's surface, because the Earth's gravitational constant is, or the acceleration due to Earth's gravity is the same everywhere on the surface of Earth, we're going to call this the radius of Earth, because the radial distance has to do with the center of a mass. So this would be to the center, the core of Earth. So the mass of Earth, we really need to know then, which is going to be 5.972 times 10 to the 24. The unit for which we want this in is kilograms, because that's going to be related to newtons. The radius of Earth is going to equal 6. We can round this. We're going to be slightly off, but if I keep some of the significant figures relatively rounded, this is going to be 6.3. I'm going to keep a few, 7, 8. The more accurate, the more significant figures I keep, the more accurate this is, times 10 to the 6. This is in meters. I want meters, I want kilograms, because a Newton by its definition is a kilogram per times a meter per second squared. In order for that to cancel out, I need the correct amount of units. I'm going to rearrange this equation. Force of gravity is equal to, I'm going to separate all these terms. G m e over r e squared times the mass of an object. Now this might start to look like mass times acceleration, right? If I'm defining this, though, as Earth's gravitational acceleration, I'm going to define it as g. So this g m e over r e squared is going to be our gravitational acceleration. And this is going to be specific to Earth. So let's plug in our numbers. We can kind of calculate that. This is going to be 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. Now it might seem tedious. I'm going to keep all the units here because I want to show you how these cancel. Let me move these over. This is then going to be times the mass of Earth. The mass of Earth is 5.972 times 10 to the 24 kilograms. You'll notice my kilogram unit cancels. If I'm looking for gravitational constant, acceleration, or the acceleration due to gravity, sorry, I keep saying that. I'm looking for the only units I better have left over are meters per second squared, because that is what acceleration is by definition. So, and this is going to be divided by my radius. This is 6.378 times 10 to the 6th meters. That whole thing is squared. So I can't just raise the power, the whole value squared, which means it is also meter squared in the bottom, which means that cancels with 2 of them. I'm just left with 1 meter. I'm left with, you'll see, a meter per second squared, which is the unit I want. That's how I know that this is set up correctly. So if I calculate that, let's go ahead and plug it in our calculator. I get 9.79 meters per second squared. So pretty darn close. You'll notice we're not exactly spot on. And the reason for this has to do with rounding errors. The more accurate the measurements, the more accurate I can get Earth's mass. Earth's mass is huge, right? So massive, like to the 10 to the 24. I can't even comprehend how massive that is. Big. The more accurate I can get that number, the more accurate my result for gravity is. The radius, again, the more accurate I get that result, the more accurate my number is. And again, you can kind of think of it in terms of an average for the radius.